This is slide number 62 and I am your presenter Asloob Mudassar. Optical transfer function and apodization. It has been established that OTF, that is the optical transfer function of an incoherent imaging system, is associated with the exit pupil of the imaging system, and that the Fourier transform of the OTF gives the intensity point spread function of the imaging system. The point spread function, the PSF of an imaging system, is composed of one central lobe called main lobe and other subsidiary lobes called side lobes. This main lobe and the side lobes will be explained later. The resolution of an imaging system depends on the width of the main lobe, whereas the contrast of an image depends on the magnitude of side lobes. Reduction in the side lobe improves the contrast of an image. So if the width of the main lobe is reduced, the resolution will be improved, and if the main lobe width increases, the resolution will fall. And what about the side lobes? If the side lobes reduce in height, then the contrast will improve, and if the side lobes increase in height, then the contrast will decrease. Researchers have found that whenever they attempted to narrow down the main lobe of the point spread function, they found an increase in the magnitude of side lobes and vice versa. So this is a very problematic thing, that if you want to reduce the size of the main lobe, then what will happen? There will be an increase in the magnitude of the side lobes and vice versa. Researchers sometimes try to engineer a point spread function according to special requirements. For example, sometimes it is required to suppress the side lobes on the left side of the main lobe, which results in the enhancement of side lobes on the right sides of the main lobe. So you see that this is one example of the engineered PSF, that what you do is that you try to reduce the side lobes on the left of the main lobe, and as a consequence the side lobes on the right hand side, that is on the right of the main lobe, will increase. So this is how you can form one engineered PSF. In the imaging of stellar objects, it may be required to resolve a feeble star lying next to a bright star, which would require a specially engineered PSF. So you see that according to different requirements, you need a specially designed point spread function, so that you can so that such a PSF can serve your purpose for which it is designed. Designing of a system PSF for a particular application would require designing of the shape of the optical transfer function, which in turn implies the designing of the pupil function of an imaging system. So you see that our main objective is to design the point spread function. But you know that the point spread function is nothing but the Fourier transform of the optical transfer function. So it means that the designing of a PSF lies in the designing of optical transfer function, and you know that the optical transfer function is connected with the pupil function, either directly for the coherent case and indirectly for the incoherent case. So the optical transfer function is indirectly related with the pupil function. So the designing of a point spread function lies in the designing of the pupil function of an imaging system. A pupil function that has maximum transmission in the center, which decreases towards the pupil edges following a Gaussian function, would produce a point spread function with slightly diminished side lobes and slightly broadened main lobes. So you see that here we are going to give an example of the Gaussian function within a pupil function. You know that the Gaussian function has a peak at the center, and it decreases slowly on both sides of that center, and you know that at the edges it becomes nearly zero. So we can use such an apodization in order to get our purpose, that is in order to get our main lobe and the side lobe controlled in a different way. So let's see what ways it looks like. So you see that in the figure you can see that this is what is this? This is actually a Gaussian profile in one dimensional, extending from -w to +w. and you know that it is defined in a rectangular aperture defined by a rect of x over 2w, because this rect has a magnitude equal to 1, which is shown, you know, that at the center of the rect. So rect of x over 2w means that rect is equal to 1 in a width of 2w. As you can see that that we have shown the rect is equal to 1, the height of the rect is equal to 1, and you know that beyond the range of minus w to plus w, the rect function decreases at once and approaches to 0. And you know that we have also shown the intensity points of the Gaussian function, which is equal to 1 over e whole square on both sides of that one. And you know that this Gaussian is actually the Gaussian optimization, which we have shown in a square people. And you know that we have plotted this one, that is the intensity through the people function as a function of x over 2w. So this is the square people aperture with Gaussian optimization. So you see that we have used the Gaussian optimization over here. Optimization is a Greek word which means removal of feet, that is the removal of side lobes of a point spread function. So you see that initially the optimization was meant to reduce the size of the size of the side lobes. Optimization is now used in more generalized fashion, which means designing of a pupil for engineered PSF. So you see that we can design different optimization techniques, different optimizations in different types of aperture, and then we can obtain our purpose by specially designing our engineered PSF. The origin of side lobe lies in the diffraction of light from the rim of the pupil. With Gaussian optimization, the edges are softened, which results in the minimization of diffraction and thus results in the reduction of side lobes. So you see that here we have given a crude justification for the reduction in side lobes using the Gaussian optimization is that the edges are softened. The functional form of the pupil corresponding to the figure shown can be expressed as. So you see that we are showing in equation number 127 the one-dimensional pupil function using a Gaussian optimization, and the pupil function has a shape of a square that is defined by a rect function. So p of x is equal to rect of x over 2w multiplied by the Gaussian function, which is 1 over sigma times square root of 2 pi, and in the numerator we have exponent raised to the power minus x square over 2 sigma square. The Fourier transform, you see that this is the pupil function. We have to take the Fourier transform of this quantity so that we can get the amplitude point spread function. The Fourier transform of this quantity is given. So you see that here you can see that we have given the Fourier transform where the Fourier of the two functions which are multiplying in equation number 127 will be convolved in the step we have shown, the first step in the Fourier transform, and you know that in the second step we have written the Fourier transform of the rect function as 2w sinc of 2w convolved with we have given the Fourier transform of the Gaussian function in equation number 128, which is 1 over sigma square root of 2 pi multiplied by sigma into square root of 2 pi in the numerator and multiplied by the exponent, which is e to the power minus 2 pi square sigma square fu square. And you know that on the left hand side we have shown p bar. P bar means that it is not the pupil function, but it is the Fourier transform of the pupil function as a function of fu, and fu is the Fourier frequency. Okay, now you know that in equation number 129 what we are going to do is that we are going to represent fu in terms of spatial coordinates. You know that fu is the Fourier frequency. It is related with the spatial coordinate u through the relation that fu is equal to u over lambda zi, which we have done in equation number 129. And similarly in the exponent we have also changed fu square by u square over lambda zi whole square. So we have obtained the final expression for p bar of fu, which is equal to 2w sinc of 2w u over lambda zi convolved with e to the power minus 2 pi square sigma square u square over lambda zi whole square. Actually, what is this? What is the equation? What is the P bar of Fu in equation number 129? Actually, it is the amplitude point spread function. And you know that to convert it into the intensity point spread function, we have to take the absolute square of this quantity, which is shown in equation number 130. Because you know that in optical transfer function or in incoherent imaging system, we talk about the intensity point spread function. So that's why we have taken the absolute square of this quantity. And you know that there are no complex quantities available, so we have directly taken the Fourier absolute square of the quantity over here, and we have taken 4 sigma square outside that one because it is a constant quantity, and we have taken the absolute square of that quantity. The absolute square is taken because the sinc function could be negative, whereas the Gaussian function is a non-negative function. So we have taken the absolute square, not the simple square, but the absolute square, because we want to avoid negative values of the sinc function when it is individually or when it is convolved with the Gaussian function on the right hand side of this. So equation number 130 is actually the intensity point spread function of our imaging system. Okay, the coordinate u is defined at the image plane. Now we are going to plot this P bar of Fu, the mod square of this quantity, versus that is you see that P bar of Fu and the mod square of this quantity is actually the point spread function, as evident on the left hand side of equation number 130. So we want to plot the point spread function, that is the intensity point spread function, or in other words the point spread function of an incoherent imaging system versus 2WFU are shown for the apodized and unapodized cases. You know that when we are talking about the unapodized case, we have to remove the Gaussian function from equation number 130. So remove the Gaussian function and the convolution sign also, and just use sinc absolute square value in order to plot the in order to make it suitable for unapodized case. So removing the Gaussian will make equation number 132 to stand for unapodized case. And you know that with the presence of the Gaussian function, it stands for the Gaussian apodization. So we have plotted these two, that is unapodized case and the apodized case, from equation number 133, which is shown in the figure below. So let's read the statement on the left. The plots in the figure show that the side lobes are attenuated. In case of apodization, at the same time the central lobe is slightly broadened. So you see that look at these two apodized and unapodized cases. You know that the plot in solid is actually due to unapodized case. That is, we have removed the Gaussian function from equation number 130, and we have just plotted the rest of the quantity. So you see that we get a solid line, plot. And you know that these dotted plots is the plot which is due to Gaussian apodization. And you know that these are the side lobes. So you know that when this is the main lobe, that is the first zero. Before the first zero, we have the main lobe on the left hand side. So we have the first zero for the dotted curve and the first zero for the solid curve. And on the left hand side of these zeros, we have the corresponding main lobes. And you know that this point spread function is symmetric on the left hand side also. So you see that this main lobe, the main lobe of those both quantities, both plots will extend on the other sides of the zero axis, and also the side lobes will also extend because this is symmetric. Now look at the first zeros of these quantities. The first zero of the dotted line occurs right to the solid curve, which means that the main lobe has increased for the Gaussian apodization. So when you are using a Gaussian apodization, the main lobe has increased, the width of the main lobe has increased. Now what about the side lobes? Look, compare the side lobes, that is the dotted line with the solid line. You will see that the dotted line has reduced height. So these are the reduced heights, you know. It means, what does it mean? It means that the side lobe has reduced when we have used the Gaussian apodization. So what we have obtained, the main lobe has increased with the use of Gaussian optimization. The second thing is that the side lobe has reduced in height. It means that if you use Gaussian optimization, you will lose some resolution, but you know that the contrast will improve due to reduction in the side lobes. Note one more thing, that the height of the main lobe is greater than the height of the main lobe for the Gaussian optimization. So the dotted line has a lower height as compared with the solid curve when we are looking at the main lobe. So you see that this is the structure, this is what happens with the Gaussian optimization. The plots in the figure show that the side lobes are attenuated in case of optimization, and at the same time the central lobe is slightly broadened. When the width of the central lobe increases, its maximum value also decreases. Optimization thus provides a control in the designing of a system point spread function. Word equivalent to optimization in other fields is windowing. So you will encounter this word, windowing. So windowing means the same, that is, you are going to apply some optimization when you are using the word windowing. So windowing could be square, could be rectangle, could be circular, and other types of windowing also possible. Okay. Now in a coherent imaging system, there is an exact relationship between the coherent amplitude transfer function and the system exit people. So direct relationship. When you are talking about the coherent imaging, there is the both, that is the coherent amplitude transfer function is directly related with the exit people of the system. Any type of optimization introduced at the exit people is directly transformed to the system transfer function. Thus in coherent imaging system, it is easier to modify the system transfer function. So just change the pupil, so just design pupil function. It means that you are able to design the transfer function directly using the coherent system. And when you have designed the transfer function, then you know that the Fourier transform of the transfer function will give you the point spread function, that is the amplitude point spread function. So it means that you can directly design the amplitude point spread function for the coherent system, direct relationship. Now you know that in case of normalized incoherent transfer function or the system optical transfer function, so in case of normalized incoherent transfer, you look at the word we are using, normalized. So the optical transfer function is actually the normalized incoherent transfer function. There is an indirect relationship. In coherent case it is direct, but in incoherent case there is an indirect relationship between the system transfer function and the system exit people. In fact, the intensity transfer function of the incoherent system is related to the autocorrelation of the system pupil function. So you see that it is related not with the pupil function directly, but with the autocorrelation of the pupil function. The shape of the intensity transfer function can thus be determined by the autocorrelation of the pupil function. Optimization is not only used for suppressing the side lobes, but it can also be used to design system point spread function according to certain imaging requirements. Optimization can be chosen to enhance the lower band of frequencies in comparison with the higher frequency bands in a transfer function, and vice versa. So let me read again. Optimization can be chosen to enhance the lower band of frequencies in comparison with the higher frequency bands in the transfer function, and vice versa. So you see that in our transfer function we have lower frequencies which are close to the zero axis, and you know that when you move away from the zero axis, it means that you are going in the direction of higher Fourier frequencies. So you see in optimization you can enhance the lower frequency, the magnitude of the lower frequencies in compare with the magnitudes of the higher frequencies. So it can also be used to remove certain frequencies from the transfer function. Selective frequency bands can also be made negative. So you see that you can make some of the frequencies to be zero and you can make some of the bands in the transfer function to be negative. Apodization thus provides a control over the magnitudes of the Fourier frequencies through modification in a system transfer function, and thus desired imaging system desired results can be obtained. The phase of the Fourier frequencies can also be controlled if apodization is based on phase coding of the system pupil function. Comparison of coherent and incoherent images. Here we would try to establish that which of the system is better, coherent better or incoherent better. So let's give some examples over here in the following topic. In coherent imaging system, the images are produced as amplitude images, which are converted to intensity images either by human eye or by physical detectors, whereas in case of incoherent imaging system, images are directly produced as intensity images. The two types of images in terms of intensity can be compared. The other possible ways of comparison between the two types of imaging systems could be in the form of comparison between point spread functions, and the second one, comparison in terms of the transfer functions. In coherent imaging, point spread function is in amplitude form, and in incoherent point spread function, in incoherent system, the point spread function is the absolute square of the coherent point spread function. The comparison of a quantity with its absolute squared would not be meaningful. Comparison of the two systems in terms of transfer functions is also not straightforward, because the coherent amplitude transfer function for a diffraction limited system is a top hat function which has abrupt cut-off frequencies, whereas the intensity incoherent transfer function for a diffraction limited system tapers off following a triangular shape with cut-off frequency twice that of the coherent transfer function. So you see that we have described the ways, we have described the reason for which we cannot compare the point spread functions of the two systems, and we also cannot compare the transfer functions of the two systems. The final product from the two imaging system is in the form of intensity images. The intensity images can be compared for spatial frequencies and for the contrast of these frequencies. This can alternatively be achieved by comparing the frequency spectrum of the intensity images from the two systems. So you see that if we are comparing the intensity images directly, there are many issues related with the two systems, because we cannot compare the intensity in the present form. That is, we cannot compare the intensity of a coherent imaging system with that of the incoherent imaging system. So the more appropriate way is to convert to obtain the frequency spectrum related with that intensity images. So when the frequency spectrum of both the coherent intensity and the incoherent images are obtained, then we have a right way to compare the system. For a coherent intensity, the equation is IC on the left hand side stands for the coherent intensity, that is equal to the absolute square of the kappa convolved with the UG, where UG is the amplitude, is the geometric optics amplitude image, and kappa is the amplitude point spread function as given in equation number 131. And for incoherent imaging system, the equation is I in subscript I in stands for incoherent and I for the intensity. Incoherent intensity on the left hand side is equal to convolution between the absolute square of a kappa and the absolute square of the amplitude image, that is k mod square convolved with the UG mod square, or in other word k mod square convolved with IG. What is IG? IG is actually geometric optics image. So equation number 132 gives you the formation by which the intensity images can be recorded. So we have given mathematical expressions for the coherent intensity image and for the incoherent image, intensity image. UG is the geometric optics amplitude image and IG is the corresponding intensity image. Kappa or K is the amplitude point spread function and mod square of a kappa is the intensity point spread function. So we have also mentioned that k is the amplitude point separated function and k mod square is actually the intensity point separated function. To find the frequency spectrum of these images, we take the Fourier transform of equation 131 and 132 in order to find the frequency spectrum of the intensity images. So you see that in equation number 131 we are going to take the Fourier transform of both sides of equation number 131. So you see that we have taken the Fourier transform of absolute square of that one. The absolute square can be written as the quantity multiplied by its complex conjugate, and you know that the Fourier transform of these two products, as in step 3, will be equal to the Fourier transform of first quantity convolved with the Fourier transform of the second quantity. And you know that the first in the fourth step we have written the Fourier transform of the first quantity, and you know that here we have converted the convolution sign with the autocorrelation sign, and we have removed the conjugate there, because that in the autocorrelation we have the complex conjugate that appears in the integral description of the Fourier transform. That's why we have removed the conjugate sign and we have converted the convolution into the correlation. And you know that in the fourth steps we have taken we have applied the Fourier transform to the individual parentheses, and then we have the Fourier transform of k multiplied by the Fourier transform of ug, because the convolution will be converted into multiplication, and then we have the autocorrelation sign, which is the asterisk sign, and again on the right hand side we have the Fourier transform of k multiplied by the Fourier transform of ug. And then the last step is Fourier transform of small k is represented by capital K. Fourier transform of the amplitude image UG is represented by GG, capital G and small g as a subscript, and the autocorrelation sign is there. Again, the Fourier transform of small k is capital K, and the Fourier transform of UG is actually capital G subscripted G, subscripted small g. This is shown in equation number 133. So let's read the statement on the right hand side. Intensity being real and positive, its spectrum will be symmetric or even function, and if one of the convolving quantities is complex conjugate, convolution will be replaced by autocorrelation. Because our quantity, you know that here is real and non-negative, and you know that this is a symmetric quantity. So if the quantity is real and non-negative, as in case of intensity, the Fourier transform will be even function. And you know that when we have the even function, then of course we can convert the convolution into the correlation, provided we are taking the Fourier transform of the quantity which is a complex amplitude. Okay. Here Fourier transform of small k is equal to capital K is the amplitude transfer function, and Fourier transform of UG, which is the amplitude image, is equal to capital G into G, is the spectrum of the amplitude image. And you know that this is the symbol, the cross symbol is represents the convolution, and the star symbol represents the autocorrelation. Now we are going to take the Fourier transform of both sides of equation number 132, so that we can obtain the spectrum of the intensity image, of the incoherent intensity image, which is shown in equation number 134. So we have taken the Fourier transform on the left hand side and the Fourier transform on the right hand side. So the convolution will be converted into multiplication as in step number 2. Then you know that k absolute square of k can be written as k into complex conjugate of k, and similarly absolute square of ug can be written as ug multiplied by its complex conjugate. Then the Fourier transform of k convolved with the Fourier transform of k convolved with the Fourier transform of k conjugate, and then again similarly the Fourier transform of ug convolved with the Fourier transform of ug conjugate. And then you know that we have converted by the same definition we have given previously, that we can convert our autocorrelation into the correlation, the convolution can be converted into autocorrelation, and similarly we can also convert the convolution into the autocorrelation in the second step. So you see that finally representing K, Fourier transform of K by capital K, and Fourier transform of UG by capital G small g as a subscript, we have obtained the Fourier transform of the intensity of the incoherent intensity, that is the spectrum that is the intensity, that is the incoherent spectrum of the intensity image on the right hand side as given in equation number 134. So we have obtained the Fourier the spectrum of the intensity image of the coherent system in equation number 133, and we have obtained the spectrum of the incoherent intensity image on the right hand side in equation number 134. The spectrum of the coherent image given in equation number 133 and the spectrum of the incoherent image given in equation number 134 do not convey any information which could help to establish the superiority of one system over the other. So you see that if you just look at these mathematical expressions, that is the expression of equation number 133 and the last expression of equation number 134, we cannot obtain any useful information. At this stage, it will be appropriate to give an example which at least could give you an idea about the superiority of one system over the other in terms of allowed Fourier frequencies contributing at the image plane and in terms of the contrast of those frequencies. So let's consider the example. We present the simulation data for a coherent imaging system, capital G and small g as a subscript, with the small g is the spectrum of the amplitude image UG and capital K is the amplitude transfer function corresponding to the square people. The spectral frequencies that would pass through the Fourier plane are given by capital K into multiplied by capital G into capital G of small g. So you see that we have assumed some spectrum. That is, we have assumed the spectrum of capital G subscripted as G shown on the left hand side of the upper row, multiplied by the capital K, which is the transfer function of the coherent system, because the coherent transfer function of the coherent system is a top hat, which we have shown in one dimensional form as shown in the middle. Multiplying these two, we are getting on the right hand side capital G multiplied by capital K on the right hand side of the first row. And you know that we are going to evaluate the autocorrelation of these two functions, that is capital G multiplied by K autocorrelated with capital G multiplied by K in the first two steps in the second row. And you know that the autocorrelation will give you the curve which I have shown on the right hand side. And that curve corresponds to the autocorrelation of GK with GK. So simulation dealing with the spectral contents of coherent intensity image. So you see that we are actually dealing the spectral contents of the coherent image, and you know that in the last step we have obtained GK autocorrelated with GK, which is the same as we obtained in equation number 133 for the coherent system. Okay, we can obtain a similar result for the incoherent system, that is corresponding to this image given in equation number 134. So we are using the same value of GG and capital G and capital K from this example, and we are going to evaluate the other things. Now the spectrum of coherent intensity image would contain spectral frequencies obtained by the autocorrelation of K into G, that is Kg autocorrelated with Kg. The data is shown in the figure is for a diffraction limited coherent aberration free imaging system. Next we present the spectrum of the incoherent intensity image. Look at this. We have taken the same values of capital G and capital K from the previous example. So look at capital G in the first row autocorrelating with capital G. With the capital G in the first row, the first two elements are showing the autocorrelation of capital G with the capital G. And you know that on the right hand side in the first row we are getting capital G autocorrelated with capital G, and we have obtained a curve that you can see. on the right hand side of the upper row. And then you know that in the second row we have GG from the previous result, that is GG on the first row, the last result we have taken in the second row, GG autocorrelated with the GG, the same result we have obtained multiplied by K convolved autocorrelated with K. So when the K will autocorrelate with K, you will obtain a triangular shape function. And you know that if you multiply the two functions together, you will get the shape more or less seems to be a triangular on the right hand side in the second row, which is actually the multiplication of the autocorrelation of G multiplied by the autocorrelation of K. So this is the simulation dealing with the spectral contents of incoherent intensity image. So you see that we have obtained two set of data. So this is for the coherent system, and we have obtained for the incoherent system this data using the same values of G, capital G, and using the same values of capital K, which we have assumed by ourselves. The graphical representation corresponding to the spectrum of incoherent image intensity given in equation number 134 is shown in figure. Now in the first row, autocorrelation of GG is computed, and in the second row it is multiplied with the autocorrelation of the amplitude transfer function. The final result shows the graphical representation corresponding to autocorrelation of K multiplied by autocorrelation of G, which tells us about the frequency distribution contained in the incoherent intensity image. So you see that this is the frequency distribution. This is the frequency distribution. The last image is the frequency distribution of the spectrum in the incoherent image. And here this is the frequency distribution in the spectrum of the coherent image. To obtain useful information regarding the two imaging systems, we have presented their final results for comparison in the figure on the next slide. I mean this figure. Before we discuss this figure, let's read the statement first. Comparison reveals. What is the comparison? So let me first of all show, then we shall read that one. So you see that in this figure, this is actually the comparison between the spectrum of the two intensity images from the two systems, that's from the coherent case and from the incoherent case. The caption is comparison of frequency contents in the spectrum of intensity images of coherent and incoherent systems. So on the left hand side we have the coherent image case. You see that we have obtained this one, but here we have shown it in the dotted line. And you know that the incoherent case is shown in the center, which we have also obtained from the previous example and showed in the solid line. And on the right hand side we are showing the two results together for comparison. So you see that the dotted line is also shown and the solid line is also shown. Both are shown together. Look at the dotted line at the foot, which is slightly extending in width in comparison with the width of the spectrum of the incoherent result. And at the same time you will see that the height of the coherent data, that is the height of the main lobe, is reduced in comparison with the height of the incoherent system. So now let's read the statement over here. Comparison reveals, number 1, coherent system has greater bandwidth because its width is slightly greater. Coherent system has greater bandwidth and allowed higher frequencies to contribute at the image plane. That is, the effective cutoff frequency of the coherent system is better than the incoherent system. This is obvious from the third image on the right hand side image. And you know that the dotted line is slightly extending, which means that it will allow more spectral frequencies to contribute at the image plane. Second step, the frequency contents lying within the pass band in the incoherent image have better contrast in comparison with the coherent intensity image. So you see that the intensity for the coherent system is higher. It means that these frequencies have got higher magnitudes, which means that the higher contrast. So the incoherent system frequencies has a higher contrast in comparison with the coherent system. Okay, comparison. Now let's are we in a position to make some conclusion about the comparison. From the comparison, that which system is better? Let's see. The comparison shows the superiority of the incoherent system within the bandwidth, whereas the coherent system has found to have effective cutoff frequency greater than the incoherent system. When spectra of their intensity images are compared, on the basis of this mixed picture, conclusion cannot be drawn in favor of any of these systems. Moreover, under different types of objects, one imaging system may behave superior over the other and vice versa. So you see that in this example we have found a mixed flavor. That is, incoherent system is superior for the frequencies within the passband, and the coherent system is superior in the sense that it will allow more Fourier frequencies to contribute at the image plane. So in one aspect the incoherent system is superior, and in other aspect the coherent system is superior. So comparison in the presence of aberration. So you see that if we take different examples, then the results could be different. So comparison in the presence of aberration, that is aberrations could be amplitude distortion, phase distortion, etc., may reverse over conclusion. Thus further investigations are required. So you see that on the type of objects and on the type of objects we can obtain different results, you know that, from the coherent and incoherent system, because here it seems that the results may depend on the type of the object. And we have also, we have not included the aberration as yet, because these examples that we have presented, these examples were for a diffraction limited aberration free system. But you know that if you include the aberrations, then the results could also be quite different. So comparison in the presence of aberration, including amplitude aberration or phase distortion, may reverse over conclusions. Thus further investigations are required. Imaging of two-point objects, point sources. Two-point objects mean two-point sources, has been used historically to stand as another criterion for the comparison of coherent and incoherent imaging systems. So you see that this is we now are going to take the two-point sources or the two-point objects. Rayleigh has defined a criterion for the resolution of two such objects under incoherent illumination. We know that the image of a point object under incoherent illumination, regarded as intensity point spread function, is an airy pattern for a circular exit pupil. So if we have a point source illuminating a circular exit pupil, then the image will be an airy pattern. So you see that, for example, we have shown airy patterns, two airy patterns on the left hand side, where we have labeled perfectly resolved. So the two airy patterns are distinct from each other, very well distinct, and you can also see their cross-sectional view at the bottom. That is, the two peaks are very well separated from each other. It means that these 2 points are very well resolved. So we can say that these are a perfectly resolved system. Now bring the two systems together, that is, bring the 2 point sources closer to each other. Then you know that when you bring the 2 point sources at the object plane closer to each other, the image points will also come closer to each other, and the airy pattern will start merging together, as we have shown in the second picture, which has been labeled as fully resolved. So again, you can look at the cross section at the bottom. That is, you can see that we can still differentiate between the two peaks, and there is also a dip, and you know that the dip is 68% lower in comparison with the peak values. Okay, if you bring the two objects closer to each other, then you know that a stage could reach which we call as barely resolved. In the barely resolved case, you can see that the two airy patterns have merged in such a way that we cannot identify any lobes separately. And if you look at the cross-sectional view at the bottom of this figure, you can see that the two peaks can be resolved, but you know that in the two-dimensional case it is very difficult, and even this has been regarded as barely resolved. So we can just very hardly resolve the two peaks in the case of a barely resolved case. And you see that there is an attenuation. You can see that the dip is how many percent? That is about 23% fall in the dip. So this is the case that you know that the Rayleigh has defined that if the dip is at a magnitude of 0.73, whereas the peaks has a height of 1, then you know that this is the criterion given by the Rayleigh that we can resolve the two objects by this one under this condition. If they come closer to each other, then you know that according to Rayleigh criterion we cannot resolve them. So you see that if the two objects come closer to each, come closer further, then you know that the two airy patterns can merge together, as we have shown in the unresolved case. And you know that the cross-sectional view as given in the bottom can be seen that there is no way that we can identify. So the object appears to be a single object with a broadened peak in comparison with the individual peaks we have shown on the leftmost image. So we have obtained on the rightmost image a single peak, but you know that a broadened peak. So this is a completely unresolved case. So you see that the maximum case is the case that we can barely resolve the two objects is given by the Rayleigh criterion under the case that the dip has got a magnitude of 0.73 in comparison with the peaks which has a magnitude of 1. So the resolution of the caption is resolution of 2 point objects in terms of their airy patterns. So let's read some statements. Corresponding to 2 point objects, there would be 2 airy patterns. Each airy pattern has one central lobe, main lobe, and around it concentric side lobes with diminishing intensities. The size of each airy pattern is greater than the size of its respective object under unit magnification system. When the 2 point objects approach each other, their corresponding airy patterns starts overlapping, and finally their individual identity is lost as they merge together. Rayleigh presented a criterion called Rayleigh resolution criterion, which explains how closely the 2 point objects can approach that they can still be marginally resolved. Rayleigh says that the 2 point objects are barely resolved if the center of one airy pattern is located at the first minimum of the second airy pattern. A dip in intensity is observed to have intensity lower by 27% with respect to the peak values. So you see that in this case, that is in the case of a barely resolved, what will happen? The peak of the first 0 of one airy pattern will fall on the center of the other airy pattern. If the two objects approach further, their airy patterns also approach each other, and the dip in intensity reduces to smaller values, thereby reducing the identification of individual peaks. The dip completely vanishes when the two airy patterns completely overlap. This corresponds to the case, the last case, unresolved case. The third image from the left in figure follows from Rayleigh resolution criterion, in which the dip is roughly 27% below the peak intensity values. When the point objects approach further closer, the dip starts vanishing, and ultimately the resolution is completely lost, which is depicted in the fourth image from the left. The width of the main lobe, however, is greater than that of the individual lobes. To give a mathematical description to Rayleigh resolution, we consider a circular exit pupil of diameter equal to 2w, which subtends an angle 2 theta at the image plane. The image plane is located at a distance equal to zi, capital Zi, from the pupil. If a point source is located at the object plane of the imaging system, the image in the form of an airy pattern will appear at the image plane. Let delta is the angular width of the airy pattern between the peak position and the first minimum, or equivalently the half angular width of the main lobe at its foot. when viewed through the exit pupil, then delta is given by. So you see that we are giving the value of delta, which is giving the half width of the main lobe, that is from the center to the first zero, and delta is equal to 0.61 lambda over w is equal to 1.22 lambda over 2w, or is equal to 1.22 lambda over capital D. So capital D is actually the diameter of the exit pupil. In the case we have mentioned that it is 2w, but you know that here it is represented by 2w is the diameter represented by capital D, as in equation number 135. And you know that if you want to go into the detail of this one, you should see one of the previous lectures. So look at this, the diagram that we have shown. So the pupil plane has a diameter equal to 2w or capital D, which subtends an angle equal to 2 theta at the center of the image plane, and we have shown only half the angle theta. So the total angle is 2 theta. And similarly we can see the angular width of the half of the main lobe from the pupil. If you look from the pupil, then the angular width of this half of the main lobe will appear as delta, as obvious from the figure also. So we have also marked the first minima on both sides of the center of the main lobes. So this is the dotted plane, is the image plane. Exit pupil subtending an angle 2 theta at the image plane. This is the caption of the figure. Now you need that we can also find out the width of this main lobe, that is delta u. This separation delta u at the image plane corresponding to this angular separation is, the angular separation is delta, we have mentioned. So according to that angular separation, the size of the image, the size of the separation delta u at the image plane corresponding to this angular separation is delta u is equal to delta Dirac delta multiplied by zi, and we have multiplied by zi. You know that on all the steps of the equation, and final result that we have obtained on the right hand side in equation number 136 is delta u is equal to 1.22 lambda zi over capital D. You know that this is delta u, that represents, you know, that the width corresponding to the delta, small delta. So this is actually the half of the width of the main lobe, that you can see that the half of the airy pattern, the delta was the angular width and delta u is the total width. The total mean that is the half width of the main lobe, because we have defined delta for the half of the main lobe. So in fact delta gives the angular resolution of the 2 point sources according to the Rayleigh resolution criterion. Generally zi is much greater than w. So you know that in our optical systems, zi, which is the distance of the image plane from the pupil plane from the exit pupil, is usually much greater than in comparison with the size of the exit pupil. So generally zi is much greater than w. That is when the theta is small, tan theta we can write it, tan theta is approximately equal to theta, sin theta is approximately equal to w over zi. So equation number 136 takes the following form. So delta u is equal to the same equation, but we have written w over w divided by zi, and then you know that we have introduced sin theta in the third step. So we have in the third step 0.61 into lambda over sin theta, and in the fourth step we have equal to delta u equal to 0.61 multiplied by lambda divided by Na, as in equation number 137. What is Na? Na is actually the numerical aperture of our exit pupil or our imaging system. So Na is equal to sine of theta, and you know that the actual expression of the numerical aperture is equal to refractive index times the angle of the sine theta. But you know that here the refractive index is equal to 1 because we are dealing in air. So we have numerical aperture directly equal to sine of theta as given in equation number 137. So Na is equal to N air multiplied by sin theta, and air is equal to 1, you know, in our case. So we have a numerical aperture is equal to sin theta is the numerical aperture of the exit pupil or equivalently of the optical system. Let's consider the two coherent point sources at the object plane located symmetrically about the origin. So you see that here now we are going to discuss coherent system for the two coherent point sources at the object plane located symmetrically about the origin. The 2 point sources can be represented by two delta functions with arguments delta of zeta minus zeta naught comma eta minus eta naught, and the other one is zeta plus zeta naught comma eta minus eta naught. Both delta functions or both point sources are existing in opposite coordinates. Let's assume that there is a fixed phase angle phi between the two sources. The intensity at the image plane can be found using the expression given in equation number 24, which takes the following form. So you see that here we are writing the intensity expression for the coherent system, which is equal to I as a function of uv, that is the intensity at the image plane, is equal to absolute square of the amplitude at the image plane, and ui, you know, that is the amplitude at the image plane due to the coherent system, and we can substitute the value of the coherent amplitude, which is equal to kappa as a function of uv convolved with ug as a function of uv. So kappa convolved with the amplitude image. And you know that we have the kappa, then we are convolving it, the amplitude image is equal to two delta functions, and we have shown these two delta functions at the imaging plane. So delta of u minus u naught, delta, you know that ug is the same at the image plane as well as the object plane. So either you use object plane coordinates or the image plane coordinates, that would not matter. So we have shown a delta as a function of u minus u naught comma v minus v naught plus e to the power iota 5, which is the phase difference between the two point sources, and the second delta function is at the coordinates delta of u plus u naught comma v plus v naught, and the absolute square is there, the convolution, the absolute square is there. So if you take the convolution with the kappa, within the curly bracket, so kappa will convolve with the first Dirac delta function, then kappa will convolve with the second Dirac delta function. And you know that phi is actually independent of the uv coordinate, so phi will not be involved in the convolution. So only delta, the arguments of the delta function will replace the arguments of the kappa function. So in the first kappa function we have the arguments u minus u naught comma v minus v naught plus e to the power e iota phi is as such there, and then we have the second kappa, which has the arguments of the second Dirac delta function, which is the kappa of u plus u naught plus comma v plus v naught. So you know that equation number 138 will give you the intensity of the coherent imaging system when 2 point sources are located at the object plane differing in phase by phi. Zeta and eta are the coordinate axes at the object plane, uv are the coordinates at the image plane. Kappa of uv is the amplitude point spread function and is given in equation number 4. Let's evaluate kappa u minus u naught comma v minus v naught using equation number 4 as given below. So here we are giving the description of kappa. How to evaluate kappa? You know that kappa is related with a over lambda zi double integral of p of xy, which is the pupil function, multiplied by this term e to the power minus iota 2 pi over lambda zi, and the arguments you know that are the same as that of kappa. We have, you know that within the curly bracket we have the same arguments as that of the kappa, that is u minus u naught multiplied by x plus v minus v naught multiplied by y, and the integration is with respect to dx and dy. Okay, and you know that the pupil function xy are the coordinates at the pupil function. So you see that this is very much the same definition as that of the Fourier transform. So the Fourier transform of this pupil function will give you the kappa. So that's why we have taken the Fourier transform of the coordinates of the kappa over there we have shown. And you know that kappa is actually the Fourier transform of the pupil function. That's why we have used the pupil function within the integral. So you see that we have separated the two integrals. in the x and y, not in the x and y variables, but you know that we have shown the curly brackets where we have shown the Fourier transform of the curly brackets, the Fourier transform of the quantities in the curly brackets, which is p of x comma y e to the power iota 2 pi over lambda z I u naught into x plus v naught into y, because u naught x plus v naught y are independent of the are not independent, but you note that x and y are there, so we have to take the Fourier transform of this quantity. So you see that this in the second step we have e to the power minus iota 2 pi over lambda z I into ux plus vy. This factor comes in the definition of the Fourier transform. So this is the definition of the Fourier transform. So you know that this integral is now giving you the Fourier transform of the quantity that we have shown in the curly bracket in the third step. So if you take the Fourier transform of the curly bracket in the second last step, it will be the Fourier transform of the people function convolved with the Fourier transform of the function in the exponent form. So this is equation number 139, where we have evaluated the value expression for kappa. So we have to calculate the Fourier transform of this exponent factor in equation number 131 and re-plug in over there, and then compute the convolution so that we can obtain the exact expression for the kappa, where capital A is the amplitude of the incident of the field incident on the pupil p of xy and is due to the single point source located at the object plane. Let's evaluate the two Fourier transforms. So the Fourier transform of this quantity we have evaluated. Look at it by yourself that we have rearranged the term, and then we have written delta as a function of fu minus u naught over lambda zi, comma fv minus v naught over lambda zi, as in equation number 140. So we have evaluated the Fourier transform of this quantity. And similarly, the Fourier transform of the pupil function is equal to the Bessel Fourier transform of the circ2 as a function of a radius r. And you know that we have already computed this quantity many times. Look at the previous and the initial, you know, that the slides to find out the detail of this equation number 141. And the final result that we have shown is J1 as a J1 with an argument of 2 pi r naught rho over r naught rho. So we have done the Fourier transform of the pupil function in equation number 141 and the exponent function in equation number 140. So let's do the convolution of these two quantities. We can also introduce rho. You see that rho is related with the Fourier frequencies in the Fourier plane. So rho is a parameter in the Fourier plane, and you know that it is related with the coordinate system, which is symmetric with respect to the origin. So rho is equal to the square root of fu square plus fv square, and r, which is the radial coordinate at the object plane or at the pupil plane, is equal to the square root of x square plus y square. So fu is related with the space coordinate as u over lambda zi, and fv is related with space coordinate fv is equal to v over lambda zi, where u and v are the space coordinates and fu and fv are the Fourier coordinates, and rho is also the Fourier coordinates. Then we have circular symmetry. So let's perform the convolution of the two Fourier transforms. So we have written the convolution of the pupil function convolved with the Fourier transform of the exponent function. Here we have shown the Fourier transform of the pupil function from equation number 141, last step, and we have also taken the Fourier transform from equation number 140, shown over here in the form of delta functions. And you know that we have represent this J1, and here there is rho. We can express rho in terms of this Fourier frequency, fu square root of fu square plus fv square, and similarly in the denominator we have the square root of fu square plus fv square. Now we are going to convolve with the delta. So fu, when convolution is done with the delta, then you know that fu will be replaced by the argument of delta functions. So fu will be replaced by fu minus u naught over lambda zi, and fv will be replaced in the during the convolution process by fv minus v naught over lambda zi. So this is what we have done in the fourth step over here, and we have rearranged the term in the fifth step. which is j1 of 2 pi over lambda zi into w multiplied by the square root of u minus u naught square plus v minus v naught square divided by 1 over lambda zi into w multiplied by the square root of u minus u naught whole square plus v minus v naught whole square as in equation number 142. So we have evaluated the Fourier transform. So now we can plug in the Fourier transform over here as in equation number 139, and then you know that we can find out the value of kappa, which we have shown in equation number 143. So this is the full expression of kappa. You know that in the coherent transfer, in the coherent image, when we were talking about the coherent intensity image, there were two kappas present. You know that, and as in equation number 138. So we have calculated one kappa. We can similarly calculate the other kappa. So the other expression for the kappa. But you know that for simplifications we consider 2 point sources in the object plane to be located symmetrically about the zeta axis, that is delta of zeta minus zeta naught comma eta plus delta of eta plus zeta naught delta of zeta plus zeta naught comma eta. Equation number 143 is simplified. So you see that we are taking the 2 point sources for simplicity on the zeta axis. At zeta is equal to plus zeta naught and zeta is equal to minus zeta naught. And you know that we have taken the 2 point sources on the zeta axis for simplicity. So you see that equation number 143 is simplified as given in equation number 144. In writing equation number 144, we have ignored the inversion of the image with respect to object. You see that sometimes we are getting the image which is inverted form of the object. So the inversion of the image has not been incorporated because we have ignored that one with respect to the object. A similar relationship for the second point source, that is the delta of zeta plus zeta naught comma eta, can be written as. So generalizing from the equation number 144, we have written equation number 145 for another source located at kappa of u plus u naught. The two-dimensional intensity expression in equation number 133 takes the following form. So you see that now we are going to plug in the values of the two kappas we have calculated in equation number 138 with the kappas which we have simplified at, because we are using the 2 point sources which are located at the zeta axis in the object plane. So this is over, you know, that the general form of the kappa from the equation number 138. So now we are substituting the values of these kappa which we have calculated in equation number 144 and 145. So the final result for the intensity at the image plane u due to the coherent system is I naught, and the absolute square of j1 of something divided by w into u minus u naught plus e to the power iota phi, and similarly j1 of 2 pi over lambda zi into w multiplied by u plus u naught. And you know that the same u plus u naught is dividing in the denominator. So this is our final intensity, coherent intensity image due to the 2 point sources located at the object plane, where I naught is equal to a mod square is the intensity of each point, so each point object. So you see that we can divide it with some quantity. As you have shown, we have divided the numerator and the denominator in some quantities by lambda zi, and you know that in order to compensate that quantity we have divided I naught outside the absolute square term by lambda zi square, because we have introduced two lambda zi within the parenthesis within the absolute square term. And you know, so that we can write this is what we have done, because we want to write the j1 as a Jink function. So the final result is in equation number 148, we have the image intensity as a function of u is equal to I naught over lambda zi whole square, and the absolute square of the Jink of w multiplied by u minus u naught divided by lambda zi plus e to the power iota phi multiplying with the Jink of w times of u plus u naught divided by lambda zi, and you know that this is the absolute square of this quantity. So this is the time where we can analyze this intensity, that is the intensity due to the coherent image. For that one, we are using some parameters which are listed. Normalized plot of image intensity is shown for 3 different values of phi. Normalized means that we can omit this I naught or lambda z I whole square. We can omit this quantity and we have the normalized intensity. And we are using 3 values of phi. Phi is equal to 0 when there is no phase relationship, when the both objects, when the both point sources are in the phase, when there is a phase of a pi by 2 between the two sources, and the third case is when there is a phase of a pi between the two sources. The data we are using in the plots is lambda is equal to 632.8 into 10 to the power minus 6 millimeter is the red wavelength of the helium neon source. W is equal to 0.0308 millimeter is the width of the aperture that we are using, is the width of the exit pupil, is the actually the half of the diameter of the half of the or the, you can say that the radius or the half aperture size of the pupil function. And Zi, because the total aperture is has a width of 2w. Zi is the distance that at which the image plane is located, and that is 100 millimeter. You can see that this 100 millimeter, that is Zi is much greater than w. And n naught and u naught is equal to 0.61 millimeter is the separation between the point sources from the central position of the image plane. So when phi is equal to 0, the two objects at the image plane are unresolved. When phi is equal to pi by 2, the two sources are barely resolved, and this case corresponds to the Rayleigh resolution criterion. And when phi is equal to pi, the dip touches the horizontal axis and the two image points are completely resolved. So you see that we are getting for the coherent picture 3 different pictures we are getting corresponding to 3 values of phi. That is phi is equal to 0, phi is equal to pi by 2, phi is equal to pi. And you know that with phi is equal to 0, we are getting a result which is shown in the solid line, the one main lobe, and of course there are we have also shown a side lobe over there. And the main lobe is very much broadened, and you can see that minus 0.61, which we have shown one delta function at this position, we have shown another delta function at the position of plus 0.61. These two delta functions represent the position of the 2 point sources at the object plane. And you know that this is the intensity, this is these 3 plots are actually the intensity at the image plane corresponding to these 2 object planes, these 2 delta functions located at the object plane. So let me first read the caption. One dimensional image of 2 coherent point sources separated by Rayleigh distance in the object space. Okay, now we have seen that when phi is equal to pi by 2, we have a dip over here. You know that this, look at this dip corresponding to the plot of phi is equal to pi by 2, where you have dotted lines, but these dotted lines are smaller dotted lines. And if you look at the case of phi is equal to pi, the longer dotted lines, you will see that the dip is touching the 0 axis. So you see that the maximum resolution is obtained when phi is equal to pi. The barely resolution is obtained, that is the resolution according to the Rayleigh resolution criterion, or according to the criterion given by given for the incoherent imaging system, is obtained when phi is equal to pi by 2. Which also stands, which is you know that stands with the criterion given by Rayleigh resolution. And you know that when phi is equal to 0, there is no resolution is obtained. That is, we have only one main lobe. We cannot resolve the 2 point sources in case of phi is equal to 0. So phi is equal to 0 corresponds to the case of a perfectly unresolved case. Phi is equal to pi by 2 resolved corresponds to the case which is barely resolved, and this corresponds to the Rayleigh criterion resolution for the coherent system. And you know that when phi is equal to pi, we have completely resolved the 2 peaks, perfect resolution, you know, when phi is equal to pi. Okay. Such behavior cannot be observed with two incoherent point sources and at the object plane. So you see that the behavior for three different values of y that we explained above cannot occur for the incoherent case. Such behavior cannot be observed with the two incoherent point sources at the object plane, and this feature is the speciality of the coherent imaging system. The two vertical lines in the figure at the location u is equal to plus minus 0.61 represent two delta functions or the 2 point sources. Look at this. These two peaks. These are the 2 point sources of the 2 delta functions. When phi is equal to 0, the coherent result matches with the incoherent result. That is, the two objects at the image plane are unresolved. When phi is equal to pi by 2 or pi, the coherent imaging system gives superior results. The results obtained in this example cannot be generalized in the broader sense in favor of either the coherent or the incoherent imaging system. So you see that here we have obtained the superiority of the coherent system by considering this example. So you see that the debate is still continued, and we are leaving the debate up to the readers that you can further investigate which system is giving you the superior results. So this is the end of slide number 62.